Hello students, welcome to lecture 17 of the online course on Nanophotonics, Plasmonics and Metamaterial. Today we will be covering surface plasmon polaritons, or in short SPP, and we will look into their fundamentals. So here is the lecture outline. So we will discuss about surface plasmon polaritons, obtain the wave equation, we will look into SPPs at single interface, the dispersion relationship of these SPPs, and we will also, if time permits, we will look into this generation, or else we will take it into the next lecture. Okay. So, surface plasmon polariton. So, what is that? So, visible light, as we know, cannot propagate through highly conductive media such as metals. When a light beam crosses the boundary into such medium, its intensity rapidly diminishes within a very short distance, which is called as the penetration depth, okay, and that is substantially smaller than a wavelength. So, a metallic surface rather acts as a mirror, right, from which light is fully reflected back into the medium or dielectric medium where the light came from. So, in the previous lectures, the metallic components have played the role of simple mirrors, right. If you remember the reflecting surfaces we were discussing, so you can think of metallic components there, and the purpose there was to simply act as mirrors. Now, if I say that metal also supports some kind of light wave, okay, so do not be surprised with that. So, typically what happens, when you see incident wave, there is a reflected wave. But there are conditions in which you are also able to excite some kind of surface waves on this metal surface. Okay. So, they actually travel along the boundaries of the metal, okay, and typically they are confined to sub-wavelength dimensions. So, such light waves, they travel along a metal surface in the form of a guided surface wave. So, it may propagate on, but not in, okay, the metallic wires. So, that you have to understand, it does not penetrate too much into the metal, rather it is mostly guided along the surface of the metal. Okay. So, they are basically useful in integrated photonic circuits as waveguides. Okay. So, you can actually transfer information across these metallic surfaces over a very short distance. Such structures can also serve as resonators within which light may be confined, or from which light can scatter strongly at a specific resonant wavelength or frequency. So, there are a couple of applications with SPPs which we have covered briefly during our introduction lecture. So, here we will go into the fundamentals of these SPPs. We will also look into some applications in the next lecture, but today's lecture will be mainly on the fundamentals. So, surface plasmon polaritons or SPPs. Okay. So, these are basically what? Electromagnetic waves. Where they travel? They travel along metal dielectric or metal air interface, fine. And where they are seen, which range they are seen? They are practically seen in the infrared and visible frequency range, and they are called surface plasmon polaritons or SPPs. So, this is the illustration of surface plasmon. Okay. So, this is the thin planar metallic film, and this is the boundary of the metallic film. On the top you have dielectric. So, what is happening here? You can see that the field or surface wave is allowed to propagate along the surface or the interface between this metal and dielectric. So, you can say more specifically that surface plasmon polaritons are electromagnetic excitations propagating at the interface between a dielectric and a conductor, and they actually decay along the perpendicular direction. So, you can understand, because they decay very sharply along the metal. So, you can only see one such representation is shown Okay, so electric field lines from plus to minus, okay, and here also from plus to minus, it is denoted by an electric field line. But along dielectric you can see that the electric field is much more extended into the dielectric region, okay, in the perpendicular direction. So this is the way they are propagating, and the field is extended more towards the dielectric region. Now this electromagnetic surface waves arise via the coupling of the electromagnetic fields, okay, to oscillations of the conductor's electron plasma. So this is where you are basically, you can actually use light to excite this kind of surface waves. So they are kind of an interaction between the electromagnetic fields, okay, to the oscillation of the conductors, in this case it is metals electron plasma, right. So this is again similar kind of diagram, but only one thing is shown here extra, that is the direction of SPP propagation, and this is what I was talking about, that in the metal they extend less, while towards the dielectric they can extend much more in the transverse direction. So in order to investigate the physical properties of surface plasmon polaritons, we have to apply Maxwell's equation to the flat interface between a conductor and a dielectric. So these are again electromagnetic waves, so they are bound to follow the Maxwell's equation. So if you remember the Maxwell's curl equations, these are the two curl equations, right. So curl of E is minus dot B dot T, curl of H equals J external, that is the external surface current density, plus dot D by dot T, okay. Now if you consider the case where there is no external charge and current density, so you can actually get rid of this term and this term, okay. So no current charge, so you can get rid of this one first, okay. So you can actually combine these two and write curl of E equals minus mu naught dou square D by dou T square, okay. That is very simple. You can take the curl, you take the curl equation here, okay. So what you get curl of E, okay, equals minus dot E of curl of B, okay. B equals mu H, so you can actually take out mu, okay, and you can write like this, okay. So you are left with curl of H, and curl of H you put from that formula by putting J external to be 0, okay, very simple. Now the curl of E can be written as, you know, gradient of divergence of E minus Laplacian of E, okay. And this particular term, okay, we can expand further, but first let us see what happens to divergence of D. D is nothing but epsilon E, okay. So you can write this as E dot gradient of epsilon plus epsilon divergence of E, okay. And if you remember that if there is no external stimulus, something like, you know, free charges, so del dot D is also 0, okay. So that you can put here, and you can simplify the equation further. So in that case this term, so this is D, so this del dot D becomes 0, okay. So what you require here, you see from this, so curl of E can be written as gradient divergence of E minus del square E. So del square E remains like this. Divergence of E can be obtained from this formula, okay. So from this equation, so this is there, this part is 0, so you can write this as minus 1 by, this epsilon will be going to the denominator, so 1 by epsilon, and then you are left with this. So in case there is a gradient of permittivity, okay, so it is not an isotropic medium, in that case it looks like this, and the right side remains like this, okay. It is pretty simple. So D is simply replaced by epsilon E in this case, okay. So you also have a epsilon naught coming into the picture, because this epsilon is basically the epsilon R, okay. So for negligible variation of the dielectric profile, that is, if you consider that epsilon is epsilon r, okay, over distances of the order of one optical wavelength, that means you are not having much variation in the dielectric permittivity. In that case, you can safely take this term also to be 0. So, you are just left with this term and this term. Okay. You remove the negative sign from both sides, what you are left with, del square E minus epsilon by c square. So, that is basically mu 1 over c square is nothing but mu naught epsilon naught. Okay. So, this is a simplified version of the wave equation. Okay. So, practically this wave equation has to be solved separately in regions of dielectric constant epsilon, okay, if there are variations in different region, okay, and the obtained solutions have to be matched using appropriate boundary condition. Now, here that is a requirement because the epsilon is not same throughout, right, because we are considering about the propagation along an interface. So, in one side of the interface the permittivity is different to the other side of the interface, right. So, we have to solve them separately in the two regions, and then you have to ensure that they are matched using proper boundary conditions. So, that is the requirement. So, this particular equation needs to be casted in a form suitable for the description of the confined propagating waves. So, let us have a look how we can do this. So, we have seen the wave equation. Now, let us try to solve this. Okay. So, we can assume a time harmonic electric field which is ERT. You can describe this as ER exponential minus I omega t. Okay. And if you put that into that particular wave equation, it looks like del square E plus k naught square epsilon E equals 0. So, what is k naught? That is omega by c. Okay. So, k naught is the wave vector of the propagating wave in vacuum. So, this equation we have seen before, this is nothing but the Helmholtz equation, right. So, now we have to see the geometry. So, the propagation geometry needs to be defined next. So, let us assume a simplicity of a one dimensional problem. Okay. So, this is basically a one dimensional problem that along z something is changing, but you have along x and y there is no variation in the permittivity, right. So, you can think of a planar waveguide kind of a geometry, and the waves here propagate along x direction in the Cartesian coordinate system, right. So, specifically if you consider this x propagation direction, okay, there is no variation along y. So, permittivity is only function of z. So, applied to the electromagnetic surface problems, the plane that is z equals 0, that is basically the xy plane, okay, that coincides with the interface sustaining the propagating wave, because the propagating wave is actually in that particular surface. Okay. So, there you can describe the electric field as Exyz can be taken as Ez, okay, exponential I beta x. So, this clearly tells you that your wave is propagating along the x direction and the electric field is basically extended here in the z direction. Okay. So, the complex parameter which is beta, okay, that is nothing but kx. So, if you think of a wave vector, your x component of the wave vector is basically the propagation constant for this travelling waves, and that corresponds to the component of the wave vector as I mentioned. Okay. So, if you take that and put this into the previous equation, you will get this is the form of the wave equation. So, now you are very specific that del square E, where is it, if you go back, yeah, this is the equation. So, del square E is now, because E is now only in the z direction, okay, and propagation vector or propagation constant you can say is only along the x direction. Okay. So, field along z and this guy is only along beta is along x direction. So, this is how you can write it. Okay. So, this becomes the wave equation for this particular case. So, you have dou square Ez dou z square plus k naught square epsilon minus beta square. So, this is the propagation constant of the wave that is traveling in this interface, okay, times E equals 0. Now, naturally such a equation also will exist for magnetic fields. So, you can have for magnetic fields, okay, just the directions would be different. So, you can take this equation as the starting point for the general analysis of the guided electromagnetic waves in any waveguide. Now, in order to use the wave equation for determining the spatial field profile and other dispersion of the propagating waves, explicit expressions need to be written for E and H, okay, that is very important. So, this can be done in a very straightforward way. So, if you remember the curl equations that you have seen previously, now if we introduce the harmonic time dependence, that is dou t as minus I omega, you can get this set of coupled equations, okay. So, these are the equations that correlate your electric and magnetic field components, okay. So, Hy is basically connected to Ez and Ey, Hy is connected to Ex and Ez, Hz is connected to Ey and Ex, okay. So, this is not a rocket science, you can go and sit down and write down the vector equations and then put those components, you will see you will get this after you apply those conditions, okay. Similarly, you can also get the other set of equations that correlate electric fields to magnetic fields, okay. So, these are interrelated equations, fine. Now, we assume that the propagation happens along x direction. So, in that case dou x can be written as I beta, okay, and we have considered that the y direction is homogeneous. So, there is no variation along y. So, dou y equals 0. So, if you put these conditions here, things get even further simplified, okay. So, the first equation that you have seen, okay, this one, so okay, this term becomes 0, this can be written as this particular form, okay. So, you can simplify these equations and directly correlate Hx to one electric field component and so on. So, all these equations, the 6 equations again get further simplified because of this condition. Now, it can be easily shown that the system allows two sets of self consistent solution with different polarization properties of the propagating wave. So, there are basically two solutions which are possible. So, the first set are nothing but the transverse magnetic TM, or you can also call P modes, okay, and in this case you are only bothered about Ex, Ez and Hy, okay. So, these are the components which are non-zero, and in the second set you are basically talking about transverse electric or S modes. So, in this case it is like Hx, Hz and Ey which are non-zero, okay. So, if you actually consider only the TM modes, you can see that the system of governing equations, so 14 to 19, so we can think of from here to here, these are the 6 equations, interconnected equations. If you put these conditions that only Ex, Ez and Hy are non-zero, then the 6 equations actually boil down to this one, okay. That is very simple, and from this you can also find out what is the equation of wave. So, this is what was not shown previously. So, this is in terms of magnetic field, okay. So, electric field was written in terms of Ez and magnetic field is written in terms of Hy, okay. So, this is how the wave equation for the TM modes look like. Dou square Hy dou z square plus k naught square epsilon minus beta square times Hy equals 0, okay. Now, if you think of the T modes, they are having analogous set. So, again remember in T these are the components which are non-zero, okay, Hx, Hz and Ey are non-zero. So take those 6 equations and put only these 3 things as non-zero, you will be left with these 2 equations, and that will also give you the T mode wave equation to be this one. So this is what we have seen earlier, right? Now with these equations you are able to investigate the surface plasmon polariton modes mathematically, because these are the 2 modes which are possible along this interface. Fine, that can give you a solution. Now let us take SPPs at a single interface. So the most simple geometry that can support surface plasmon polariton mode is nothing but a flat interface between a dielectric which is non-absorbing, okay, on one half, that is we can split the space with a boundary at z equals 0. So z greater than 0, you can take that half space to be dielectric, non-conducting, non-absorbing as well, and the bottom half you can think of, z, that is z less than 0, is nothing but a conducting half space. Fine. So this one you can take a real dielectric constant, that is epsilon 2, whereas metal usually have a complex dielectric constant, and that has got also dispersion. So metal does not have a flat dielectric profile, so you can actually take it as a function of omega. So you can take this as epsilon 1 omega. Okay. Now the propagating wave solutions, they confined to this particular interface. Okay, that is, we have assumed that the evanescent fields are basically decay along the z direction in both cases. So if that is the case, let us first investigate these 2 hubs separately. First let us look into z equals 0, that is into the dielectric region. So these are the equations we have understood, that for this particular case Hy, Ex and Ez are non-zero, and we can write the equations to be like this. Okay. So that is for z equals 0. So if you consider z equals, z is less than 0, in that case all these z's will be actually replaced by minus z. So here if you put z equals minus z, okay, so you get the equation in this particular form. Okay. So I would recommend you guys to write down the equations on a piece of paper to look at them at the same time, so that will possibly help you to understand this better. Okay. So these are basically which are these equations. Okay, what are these values? So if you go back, you have your answer here. Okay. So Hx, Hz and Ey. Okay. So that is for TE modes, and if you look into the TM modes, look at the TM modes, Ex, Ez and Hy. So these are the 3 components that you require, and these are the 3 components that has been described here. So we are basically discussing about the TM modes in this case. Okay. So with that, what we figured out, that Ki can be written as Kzi. So I is nothing but 1 and 2, that is that this 2 particular region. So this is 1, this is 2. Okay. And you can also find out that it has got a reciprocal vector that can be described as z cap, which is 1 over modulus of kz. Okay. So what is kz? That is the component of the wave vector perpendicular to this interface between the 2 media, and you can also think of a reciprocal to that particular vector, and that defines the evanescent decay length to the field which is perpendicular to the interface, and this also quantifies the amount of confinement along the each side. Okay. So if you actually discuss about the continuity of magnetic field and electric field at the interface, okay, you will see that this 2 amplitudes A1 and A2, they should be same. So what are these 2 amplitudes? So these are the amplitudes described here. okay, and they should be same. Okay, I am not going into the exact details of each of this. So, that poses the requirement that K2 over K1 should be equal to minus epsilon 2 over epsilon 1. That means the two permittivities should have opposing values. Okay. So, with that convention you can write that the confinement to the surface, what you have seen here, that demands that the real part of permittivity of epsilon 1 should be negative if you want the other one to be positive. Okay. So, that is possible when you choose one as metal and another as dielectric. Okay. So, that is what we understood, that a metal dielectric interface will actually be able to support surface plasmon waves. So, in that case the expression for Hy gets further simplified and that has to further fulfill the wave equation, and that gives you these two values of Kz. Okay. So, K1 square, that is the component of the wave vector along this interface, this one in the metal, and this will be K2, that is the component of the wave vector along z direction into the dielectric. So, you can actually obtain these two values. Now, if you combine these two these equations, this ratio and these values, from here you are able to obtain the dispersion relation of the surface plasmon polaritons which are propagating along the interface. So, you can obtain what is beta, that can be written as K naught square root of epsilon 1 epsilon 2 over epsilon 1 plus epsilon 2. So, that is a very important relationship that defines the relation between the propagation constant and the frequency. Okay. Now, you must be wondering where is the frequency term here, where is the propagation constant term here. So, beta, if you remember, this is basically the propagation constant along the x direction, right. So, this is basically where the k part is coming from. Okay. And then epsilon 1, as I mentioned, epsilon 1 is implicitly epsilon 1 function of omega. So, this is where this creeps in. So, you actually get omega k relationship, that is this dispersion relation for SPPs propagating along this particular interface which is in x direction. Now, this expression is valid for both real and complex omega 1, that is for conductors with or without attenuation. So, you may think of a metal which is lossless, in that case also it will work, okay, but that the requirement is that you need to have this one satisfied. Okay. K2 over K1 should be equal to minus epsilon 2 over epsilon 1, this has to be satisfied. Okay. Now, before we go into discussing the dispersion relation and what exactly it conveys, let us also have a look into the possibility of TE surface modes. Okay. So, this was what we have seen is for the TM surface modes. Now, similar kind of approach. So, we will start with the TE set of equations, that is basically equation number 23 to 35. Okay. So, in each case we have to see that what happens for the TE modes. So, we will be only discussing with those components which are non-zero for TE case, and that is basically EY, HX and HZ, right. And we write this for Z equals 0, also we write it for Z greater than 0, that is in the dielectric. We also write the same sort of equations for the space Z less than 0, okay, that is what happens in the metal. Okay. So, direct correlation, because here this figure, this one and this one are on the same page, so I will be able to compare it. So, quickly you see how they are different. So, Hz function of Z equals A2. So, A2 is the amplitude in the dielectric, in metal you have the amplitude of A1, okay. So, this is a parameter that is different. Then you have beta omega mu naught, that remains same, Propagation constant is also along this one, so that remains same, e to the power minus beta x, e to the power minus beta x, that is fine. What is different? The decay constant in dielectric is e to the power minus k2 z, that is fine. Okay. Now in this case z is greater than 0. When z is already negative, you can replace this minus z by z because z itself is negative, so you simply have z, and the constant, decay constant in metal is k1. Okay. In dielectric it was k2. So this is how you can actually see the equations are being different. Okay, that's all. So all these equations here are A1, A1, A1. For dielectric you will have A2, A2, A2. Okay, very simple, similar to the previous case. Now if you look into the continuity of EY and HX, okay, across the interface, so these are the two components, you have to see they are continuous, then this is the condition that comes out to be. So you will get A1 times K1 plus K2 equals 0. So if you take that particular condition, we have to see what can give us that particular this particular condition. Okay, what actually gives us that? So since the confinement to the surface, now you have to make sure that there is confinement on the surface, so you will require that the real part of this K1 is positive and also real part of K2 is also positive, then only they will be confined along the surface. Okay, so this condition can only be fulfilled if A1 is 0, and if A1 is 0, A2 also becomes 0. That means there will be no amplitude possible when you are considering the TE polarization. It means no surface modes can exist for TE polarization. So in simple word, we can say that SPPs are only TM polarized waves. Clear? Okay. So once we understood that SPPs are purely TM polarized waves, and we have also seen a glance of their dispersion relation, let us look into the dispersion relation and see what it actually conveys. Now here is a plot, okay, dispersion relation of the SPPs. So at the interface between a Drude metal with negligible collision frequency, so you can think of as almost lossless, okay, but it is having a negative permittivity, but it is lossless, it is a real one. Okay. So Drude metal permittivity you have seen previously in the previous lectures. If you take gamma, that is the collision frequency, to be 0, your Drude metal permittivity will be simply epsilon 1 function of omega will be nothing but 1 minus omega p square by omega square, as simple as that. Okay. So if you take that and you consider the two cases, in one case it is this Drude metal and air interface, in other case it is this Drude metal and silica interface. So the air interface, you are drawing it using gray curves, so these light color lines are basically for that case, and if you see the black curves, they are basically for the metal silica interface. Now this we have seen, this is the dispersion relation. Okay. So now what are the parameter values for epsilon 2? If it is air, epsilon 2 is 1, and fused silica, if you think of fused silica, epsilon 2 is nothing but 2.25. Fine. Now in this particular plot, you see one thing, that the frequency is basically mentioned as a normalized frequency, and normalized to what? Normalized to the plasma frequency of the metal. So this kind of graph you can use for any metal. If you actually know the plasma frequency, you can actually find out what is the frequency, actual frequency we are talking about. So this is a normalized one. Again, the wave vector is also a normalized one. You can see it is basically beta c over omega p. Okay. Now here what is happening, that the solid curves that you see, they are basically the continuous curves, they are the real part of the wave vector beta, and if you take the dotted part or the dashed part or the broken curves, they basically correspond to the imaginary part of the beta. Now, due to the bound nature, the SPP excitation correspond to the part of the dispersion curve that lie to the right of the respective light lines. So, these are basically the light lines. So, here light lines means here the dispersion relation is simply omega equals Ck, okay. And this one, what is the dispersion relation for this one? Omega equals C by n times k, okay. So, these are called the light lines, okay. So, you will see that in both case the SPP relation are basically lying towards the right of this, okay. Now, if you look into the case that they do not exactly match. So, for air you see there is no case where there is a direct matching of momentum. So, you can take this as a momentum vector or k vector. So, for a given energy you will see that there is no match between the momentum of the SPPs generated in the air interface with the photons that are in the air, okay. So, you have to do some kind of phase matching or momentum matching using some techniques that we will describe maybe in the next lecture, okay. And we will see how we are able to excite surface plasmons on air interface or silica interface. So, for silica, this black line you have to look into this particular line as your light line. For SP in air interface, this curve you have to look for this particular gray line, okay, fine. Now, there are certain regime in this particular graph which also needs special attention. First of all, radiation into the metal occurs in the transparency region. So, what is the transparency region? When the frequency is more than the plasma frequency, that is when omega over omega p is greater than 1. So, this particular is region. So, if you draw a imaginary line, horizontal line at this omega by omega p equals 1. So, anything above this is basically the transparency region, okay. So, in that case the radiation into the metal will occur in the transparency region. Now, between this region and the bound mode, so these are basically two bound modes, the SPP modes, okay. So, there is basically a region like this. You see here no solid lines are possible, and what is only possible here is nothing but purely imaginary beta. So, imaginary beta does not allow you propagation, right. So, there is basically a frequency gap region, that this particular region you are not able to excite any mode. Now, if you look into the region of small wave vectors here, so when the wave vector is small, okay, that is you can consider about mid infrared or lower frequencies, okay, you can see that the SPP propagation constant is very close to k naught. So, k naught will be the propagation constant in the light lines. So, you see here they are very close, the curve and the straight lines they are almost overlapping, okay, and the waves they extend over many wavelengths into the dielectric space, okay. But in the regime, okay, in this particular regime, SPPs therefore acquire the nature of grazing incidence light field, okay. So, here it is more or less at very small value of wave vector, SPPs have very similar k naught as the light lines. And if you look into the opposite regime here where the wave vector is very large, in that case, okay, the frequencies of the surface plasmon, they actually reaches a saturation kind of thing, and that is basically the frequency of surface plasmon resonance, okay. So, that is a characteristic surface plasmon frequency at a particular interface, and your SPPs will actually try to go and reach that particular frequency. Okay. Now, what is the good thing about this is that for a given frequency, you are able to get SPPs with very large wave vector, okay, or wave number. So, that actually allows you to have very short wavelength, and this is where the amazing thing about SPPs are. For similar frequency, you are able to have wavelengths which are very tiny. So, you can actually confine electromagnetic radiation into those small region, or you can manipulate electromagnetic radiation in that very small scale. That is not possible by photons. So, that is why, so these are light lines. Okay. So, here omega equals Ck, that is it. So, there is a relationship between the frequency omega and the lambda. Okay. It is a linear relationship. But when you come here, they are having a non-linear relationship, and that allows you to basically do this wonder, that for a given frequency you are able to bring your wave vector as large as possible, or you can say wave number as large as possible. That allows you to have wavelength very small or as small as possible. It cannot be infinitely small because there is a saturation here which corresponds to the surface plasmon frequency, and this is the wonderful thing about SPPs. Okay. So, you can actually see that what is the characteristic frequency omega SP? It is the plasma frequency divided by square root of 1 plus epsilon d, or epsilon 2 in this case. Epsilon d is the dielectric permittivity, here epsilon 2 is that permittivity, right. So, these are the cases. Let us quickly look into this. So, surface plasmon polariton wave at metal dielectric boundary, this is what we have seen, that this actually propagates along the boundary, high low high low high low and so on, but the field extends more into the dielectric region, less into the metal. This is how it is propagating nicely. Now, if you look into figure 2, figure 2 actually plots the good things about, okay. So, here there is a reversal in the denomination. So, the parameter for dielectric is epsilon 1 here. So, let us consider epsilon 1, okay. So, it is a positive value, so you have drawn it here. Epsilon 2 is negative because that is the metal. So, let us plot this one. So, if you remember the Drude model, so epsilon 2 in this case will be 1 minus omega p square over omega square. So, at omega equals omega p, the value is 0, okay, and at omega equals omega s, you will see that this value is same as minus epsilon 1, and this is the resonance. Okay. So, the frequency dependence of the permittivities of the dielectric and the metallic media are shown in this case, and the condition that modulus of epsilon 2 should be greater than epsilon 1, that is required, and that is satisfied for omega less than omega s. So, if you have frequency below this, okay, this is the case, this is the region where your SPPs will exist. And figure 3 is basically the dispersion relation we have just seen. So, this one, as I told you, this allows transparency. So, this is basically the bulk surface plasmon, or you can say bulk plasmon polariton BPPs, okay, and these two dotted ones are the light line. Why the slope is different? Omega equals C by N times K or beta, okay. So, that is why the slope for silica is different than air. The air one will have the highest slope, and this is how it actually gets saturated towards omega s, that is this particular characteristic plasmon frequency. So, in this case omega s is omega p over square root of 1 plus of epsilon 2, or sorry epsilon 1 here, because permittivity is 2.25. So, you can do this calculation, it is 0.55 times omega p. So, you can mark this point. So, this is the final value towards which this curve will approach. Okay. I believe this particular concept is clear. So with that we will stop here today, and in the next lecture we will look into the mechanism of exciting surface plasmon polaritons and some of their applications. So thank you. If you have got any queries, you can drop an email to me at this particular email address mentioning MOOC on the subject line.